Hey y'all, in today's video we're going to explore things called rate laws. Rate laws are expressions where we can mathematically determine the rate of a chemical reaction utilizing the variables of concentration along with something which is known as the rate constant. We're also going to deal with things called rate orders, which are based on exponents that are unique to each reactant in a reaction equation. So let's go ahead and start by looking at a rate law and identifying the different elements of the rate law. So if we look at this generalized rate law, this is actually only going to be a rate law with one reactant shown, reactant A. Rate laws always start with rate equals and then a lowercase k. That lowercase k represents the rate constant, and the lowercase k is going to be determined using something called the Arrhenius equation, which we're going to explore a little bit later. But essentially, you can think of that lowercase k as the probability of the reaction occurring. So this goes back to activation energy and likeliness of effective collisions. The bigger the k value, the faster the rate overall. The concentration is represented by brackets, and therefore this is the concentration of A raised to a power of m. Now, the concentration of A, you'll notice, is just one concentration. That's because this is going to show us the instantaneous rate of the reaction at any point where A is that concentration. The power that you see, the exponent that you see, the power of m, represents the order of the reaction with respect to A. The higher that number is, the greater the order of the reaction with respect to A. Normally, those exponents are integers, 0, 1, 2, 3, etc. However, they could be negative and they could be fractional. Okay, so just so you're aware going into this that they can be integers, fractions, or negative. But in general, they're going to be positive values and integers. Let's figure out how to use data to determine the rate law of a chemical reaction. Normally, you're going to be provided with data that looks a lot like this. You're going to have multiple trials, as well as the initial concentrations of your reactants and the initial rate. Remember, the initial rate is the instantaneous rate at time equals 0. So if we look at these different trials, any good scientific experiment is going to hold all variables constant except for one, which will be changing. In this case, we can make a comparison between trial 1 and 2 and see that in trials 1 and 2, only the bromine is changing. The bromine doubles between trials 1 and 2. Simultaneously, the nitrogen monoxide is held constant. Now, that means that any change in the rate of the reaction must only be due to the change in the concentration of the bromine. So the bromine concentration doubled while the nitrogen monoxide was held constant, and the rate doubled. This means that the rate of reaction is proportional directly to the rate of change of the bromine, or the rate of to the concentration of the bromine. Now, at the same time, if you look at trials 4 and 5, in trials 4 and 5, the bromine is held constant while the nitrogen monoxide has been doubled. Now, that means that any change in the rate at that point must be due to the change in the nitrogen monoxide. And if we look, we can see that the rate quadrupled. So in this case, the rate was proportional to the change in bromine, but it's proportional to the square of the change in nitrogen monoxide. So when I see this little fish symbol, it means proportional. So the rate is proportional to the bromine concentration and proportional to the nitrogen monoxide concentration squared. Okay, because when the concentration of nitrogen monoxide doubled, the rate quadrupled. Okay, 4 is the square of 2. We can actually combine these so that we can see the rate is proportional to the concentration of bromine times the concentration of nitrogen monoxide squared. They each had their independent effects, but if we combine them, then they would have an additive effect or a multiplicative effect in that case. Now, if we look at this, I don't like that proportional. I want it to be equals. And that's where that K value comes in, that rate constant. Because the rate constant is how we're going to go from rate is proportional to rate is equal. So what we write here is that the rate is equal to K times the concentration of bromine times the concentration of nitrogen monoxide squared. This means that the reaction is first order with respect to the concentration of bromine and second order with respect to the concentration of nitrogen monoxide. So when we're calculating the rate law using initial rate data, we can do this in the form of a conceptual manner, but you have to be careful with the conceptual manner. You can't just say, oh, this doubled, so the rate doubled, therefore it's first order with respect. You have to be clear and concise. You have to say the bromine doubled while nitrogen monoxide was held constant. Therefore, the rate law shows that it's first order with respect to the concentration of bromine. See, because what happens if you change two things and you don't account for that in your justification? You have to. We're also going to learn about how to do this using a tool called logarithms. In that case, we're actually going to solve for it mathematically. That's what's going to give us the power to be able to solve for these exponents in the event that they're negative, or in case they're fractions, or in the case that they are numbers that we wouldn't necessarily be able to calculate in our heads like we could in this situation. The other thing to be aware of is that we can actually determine the overall rate of a chemical reaction by simply adding the orders of each reactant. So in this case, the bromine was first order, that's a 1. The nitrogen monoxide was second order, that's a 2. So the overall order of this reaction would be third order. That plays a much bigger role when we're talking about the K than anything else. And we'll talk about calculating the units of K here in a moment. Now, in the end, rate of a chemical reaction is always measured in the units of change in concentration over change in time. So molarity per unit time. Now, the K value is going to connect the changes in concentration to the rate. Remember, this is how we went from being proportional to being equals. But that means that it's not only the values that have to connect, but also the units that have to connect. Oftentimes, you're going to be asked to solve for the units of K alongside the value of K. What that means is we simply have to make sure we're accounting for units. When we have a first order reactant, its unit of concentration is going to be moles per liter. But a second order reactant is going to be moles per liter squared. This means it's moles squared per liter squared. So if we look at the overall order of a reaction, we can make a decision based off of what are the units of K going to be. If your reaction is 0 order, that means the exponents of all of the reactants are 0. That means molarity raised to the 0 power, which is just 1. So the rate in that moment, being moles per liter, is equal to the units of K, moles per liter. For a first order overall, it gets a little trickier, because if you think about it in terms of rate equals K times concentration raised to the first power, when we solve for the units of K, we multiply both sides by liters and divide by moles, which gives us just inverse seconds or inverse time, right? Sometimes our rate isn't in seconds, sometimes it's in minutes or hours, in which case it would be inverse those values, those units. But a first order overall reaction would have a K unit of inverse time. Second order, we're now going to be solving with a concentration of moles per liter times the concentration of moles per liter, so moles squared per liter squared. We multiply both sides by liters squared over moles squared, and what we end up with is inverse molarity, liters per mole, and inverse time. So you can think of it as molarity to the -1 time to the -1 in the case of a second order overall. This would continue for third order, fourth order, etc. as we keep building. The units of K can be solved for very quickly and easily, and I wouldn't recommend memorizing it because I just don't feel like it's extremely helpful. If you know your algebra and you know how to solve for the units, you'll be just fine. without having to actually memorize the units of K for every order of reaction. So that wraps up today's video. Today we use tables to determine the rate law of a reaction. And remember, the tables are going to show us the initial concentrations and the initial rate of the reaction. In order to use tables by themselves conceptually to determine the rate order, we need to make sure we're holding one reactant steady and constant while the other is changing. We then use the proportional effect of the change of the concentration versus the change in the rate to determine the rate order with respect to that reactant. The overall rate order of the reaction is simply the additive of the actual orders of each individual reactant. We then determine the actual value of units of the K for any rate law. In future videos, we're going to start to implement this in a more quantitative way, and we're going to start learning some new techniques just in case the rate orders aren't integers that are easy to solve for, like 0, 1, or 2, but instead perhaps when they're fractions or even negative values. That's it for this video, and I'll see you in the next one.